Good morning, morning. A few words about myself. I'm Rafał Szarecki. I work for Juniper Networks since 2006, last 6 years in the Bay Area. This presentation is about the techniques big word, invented or used last year to deal with one of our key customer challenge, which tends to be how we can control the state explosion of best guess protocol, border gateway protocol, in a specific environment, which I would say it's a scale-out peering. So, if you have any question during the presentation, well, just break me. I prefer interaction. So our agenda is like, first, what is the environment? What is the scale-out peering? Why? What is how it's what it is? What is not? Why it's so specific? And what are the principles of operation? This will lead us to the control plane challenges, right? So the BGP scale and limitation of the well-known common practices. And finally, I want to share with you the solution solution for that with the critical construct of the abstract next hop, what it is, and how the internal BGP architecture will look like when we use the abstract next hop. Abstract next hop is, by the way, my term, so we can always change it as community over time. And finally, some configuration examples. This is not a marketing presentation, so I would say I would try to keep it very short, but we spend more and more time on the devices with the screen. Our application even if screen is dead, like my iPhone, the application are running in background. The message is coming. The notifications are coming. So the bandwidth is growing, especially the need for bundling and also round trip delay. Right? That is equalized to experience how my experience with the application, with the web page, with the app is, and this, in addition to the fact that the consumer of the data and producer of the data is usually different network, Facebook and T-Mobile, or whatever operator. This leads to the situation when the peering is more dense and dense. It's more points, more connection, more bandwidth needed. And that's why not only we are generally seeing at least from place where I am at Juniper Networks, we are seeing this interest in the scale-out architecture where we have good resiliency without extra cost because it's N+1 resiliency. We can provide the capacity and scale the capacity as needed. And by reducing the requirements for the bandwidth, bit density on every element in the network, it's just good for competition, right? It's easier to use different products. So what is this scale-out peering? I try to put this kind of formal definition. So if we have a given PRIS connected to multiple autonomous system ASBRs at given site, and that's the situation when we have a scale-out peering, right? We peer with the given PRIS in the scale-out manner. And then, of course, the whole routing system is set up to enjoy the ECMP downstream and upstream. Of course, there is a limits, right? The PRIS can do whatever he wants with the policy, but conceptually, I'm advertising on all 4 devices down to the PRIS, my network equally with the equal attributes, and expect the same opposite. And the scale-out peering is specific subcase or subset of distributed peering, right? We may have the different environments where the given AES is connected to two ASBRs at different sites, or two ASBR at given sites connects to different peer AESs. That's distributed peering, right? We distribute the peering load, but it is not scale out, at least not in context of this presentation. So if we have a peering site with a scale-out peering model, we have the bunch of ASBRs, we just discussed that. We will have also the set of core routers or core switches, whatever we call it, spine even. That's in this year or last year fancy name of the core device. And probably root reflectors, and we will talk a little bit about them later. And in between, there needs to be something which connects this. It connects these elements in a way which allows me scale out peering, so add the peering devices without impacting the rest of the network. And in general, this something in between could be a passive network, just like cables, or some active elements. L2 switch is the simplest example, or sets of switches. That's a little bit vintage. It could be L3 underlay network, 5 stages clause. It could be just pure L3 device, flat. Or probably there will be more possibilities. However, if we look how it looks from how this behaves from the routing perspective, how this option behaves from the peering, so internet routing perspective, 3 out of these 4 ends up with the same situation when my core routers and the ASBRs are directly peering at layer 3, right? If we have overlay, there are tunnels. If we have L2 switch, we have segments. If we have passive network, we have closed topology. If we put like on the bottom right side, some active elements with the full capabilities of the internet routing in the middle, it's nothing else than just a bigger closed network. So like a hierarchical core, if you like, or spines and core leaves. That's a little bit back to the future. When I draw it first time, I say, hey, I saw this somewhere. And look my CCIE book from 90s. I say, yeah, core distribution access, the same. But just a side note. For the rest of the talk, I would rather, we will talk about the topology on the left upper side, just because it's the simplest. But everything is valid in all other cases. So what are the common principles when we go to the scale-out peering, right? We want bandwidth, we want write on the ECMP. So what will be impact on my network, on my control plane? Equal cost load balancing among ASBRs. That implicitly means that we have to use best BGP multipath. In some point in the network, the BGP routing will be across multiple gateways, load balancing. And that scale up the RIP, routing information base. Yeah. If we say, okay, I have 500,000 prefixes for gateways, it's ultimately 2 million paths, just like that. The second, we want to write on N+1 redundancy model, right? So if one fails, we are losing only proportion of the capacity, and we can over provision like a 20% of 25% instead of 1+1. That's a big financial gain. And this has to be, the redundancy has to cover us against the inter-AES interface failure, also multiple session failure, because we don't know what is on the opposite side in the peer AES. So single failure on the peer AES can appear on my AES as a multiple session down. My ASBR failure and the entire site could go out. Hopefully never, but Then I want to scale out, I already said it. So be able to add additional ASBR on one side without impacting the other. So it has obvious consequence on the physical network. If I add the, I don't want to add the links across the entire global network, but also on the control plane, right? Using the 2 or very few core routers at site, I can keep scaling out the ASBRs. But scaling out ASBRs mean also scaling out the number of path in the BGP. And now I can say in this remote region somewhere in Alaska, I have my old router, right? And I don't need to upgrade them. There is enough capacity and enough interfaces, but because my routing information base scale up, I need to hardware upgrade that router as well. That's not what I want. So my network-wide solution should isolate this scale out at the site from the rest of the network. And ideally, I would like to restore the traffic in seconds rather than in tens of minutes. That's a general call to avoid or try to mitigate situation when my convergence of network is really dependent on the per prefix, per path withdrawal and re-advertisement. It would be much better if we can do this in the bulk. So that's what we want. And how the traditional or typical BGP design will deal with that. First, look at the scale, right? If I have the network of 40 sites, 4 ASBRs, two root reflectors, each ASBR gets from peer AS to 500,000 prefixes, not that much. Only half of it is active because the other half is better from the other exits. 1 million active prefixes is also not out of the reach. Looking globally on the network, it means that the network learns 80 million paths. And we have, globally, we have 80 paths per prefix. If I want to use the ECMP, I need the add path. If I do the crazy add path 80, I don't know if any hardware can do that, but that leads to the situation when I have like 80 paths, out of which 4, maybe 8 is active. Another 4, maybe 8 is my backup or second best path if you use something like BGP peak. But 80% of this information is just not needed. It's not primary, it's not backup. Why to keep it across the network? And the BGP without add path is doing this nicely. Just select the best active path and that's it. But if we do the add path for the multipath ECMP load balancing, then we have this challenge. The other thing we cannot forget is that we have limited control of what our peering AS is doing. Right? We assume they advertise all prefixes on all links because they also, my peer AS also like to use the ECMP characteristics, but people make mistakes. And policies always could be put there for whatever reason. So it could happen that some of prefixes doesn't exist on every, do I have this? No, laser, on every session, on every ASBR. And this leads to some trade-off, right? Either we need to have something smart deep in the network, like a core router, which is able to do the full IP lookup and knows where to send. It's still a ECMP over 3 for the prefix number 2. Or we have to agree on some suboptimal routing on the egress side when one ASBR will drop the traffic to another ASBR. I believe that the optimal routing is our goal. This is the way how we control the cost and latency. So that's the underlying decision was what we go with. And by the way, the customer we work on with that, who triggers that work, anyway is doing IP routing on every device. So. And finally, if my peer AS is doing the same as I'm doing, so going scale out, the number of sessions will grow. Come on. So we will have to reduce the number of BGP paths across the network. We will need to have ECMP, and these two are kind of contradictory requirements, and enables some fast convergence or sub-second restoration. Sub-second, maybe this is what we almost achieved in the particular scenario, but a restoration of traffic in seconds, not in tens of minutes. That's what we tried, what we can achieve here. And to go deeper into the solution, this will be my reference network with some naming convention where there is a role, there is a site, and there is a number of devices at site. The entire network is doing native IP forwarding. We have the root reflector, which are connected in two full meshes. So the first root reflector at given site, full mesh with first reflector on all other sides. Root reflectors are running multipath and add path with their clients, so the core routers and ASBRs. Toward other root reflectors out of sight, we will advertise only a single path, just to prevent the situation when our 80 million path goes across this entire net system. ASBR accept the multipath, accept add path from root reflector, but when it speaks to root reflector, it advertises only best route. So the first typical deployment we have today is using NextHop Self. How many network is using NextHop of your network is using NextHop Self? Just 2? 3? Okay, 4, 5. Good. With that, before a failure happens, everything is perfect. I just want to highlight that the core router has the 4 paths to 4 local exits, and all the next hops are loopbacks of the ASBR 1.1 up to the ASBR 1.4, and all these loopbacks are in IGP. So what happens if this link fails? All 4 loopbacks are still in IGP. And ASBR 1.1, the one which is impacted, obviously will withdraw the routes. We'll send the withdrawal to the root reflector. For 500,000, it takes some time. Tens of seconds, minutes, depending on the hardware, right? And what else is going on in the network. Root reflector reflects this information back to the core routers, and the core routers remove the path and updates their FIP, which takes another X minutes. And then routers at the other sites may need to do exactly the same thing, right? If this path, particular path, was the one chosen as a best from root reflector, probably based on the router ID, then this churn need to be propagated. Okay, so maybe using the NextHop unchanged is the better behavior. But in this case, again, we have 4 NextHops because of the passive interface, passive IGP on the external interfaces. All 4 NextHops are reachable through the IGP on the core routers, and the failure is a session down, not interface down. Unfortunately, NextHop stays in the IGP, and the story repeats. We have to withdraw all 500,000 prefixes, or whatever the number is. It takes time. You may say, oh, it's overkill. How it happens that session goes down and interface is up? It could, if you have a switch in between, if you have some old DWDM system in between. But even we have a situation when actually interface will go down. The mechanics is that traffic at site 3 will be moved to the suboptimal path, right? Because the next hop is removed, and the route reflectors and core routers and the ASBRs at site or whatever edge routers on the site number 3, by some time running with has invalid BGP path with the unresolvable next hop, so they will select another one. And I said that before that the route reflectors propagate only one best path out of their site. So from site 3, the alternative path is via site 2. And then, of course, there is a BGP convergence with drawal updates, etc. So traffic comes back to site 1 because it's closer in the IGP. But we have these traffic shifts. Not nice. This could be avoided if we run the add path between sites. But then it's a cost which we try to reduce, right? The scale of the BGP routing information base. And it's not only the memory, but it's also the time of the cold startup, right? When we start from scratch, it's 4 times more information to be carried between sites. It's also a challenge with the churn exposure because we have 4 paths, and if 4th best path or 3rd best path is flapping, it doesn't really change anything in the network, but we have to propagate this information and consume resources, CPU resources. Okay, so I think the most interesting part. Come on. Okay. The solution is based on the construct I called abstract next hop. So first of all, this is not a change to BGP. There is no protocol change. We use exactly the same old BGP protocol in terms of how we encapsulate the frames, in terms of what is the semantics of every attribute, and in terms of the BGP selection algorithm. No changes to BGP. The abstract next hop is a /32, /33 would be, or /128, obviously, address, which is set as a BGP next hop in the advertisement. If the advertisement is, if the path was learned from one out of the set of BGP session, right? So this is like an option to group a couple of BGP sessions and say, okay, fine. If at least one of them is advertising this prefix, I will keep using this as a BGP next hop. So it's a little bit similar to the loop, the next hop self, right? We change the next hop, but at the same time, this abstract address, this address is in my IGP, advertised to IGP, conditionally, only if at least one session is up and running. If the session goes down, all session in group goes down, I remove the next hop from the IGP. And what is this subset of session which is associated with the abstract next hop? It's up to you. It's a part of this network design. It could be all session from given ASBR with the same PRAS, but it could be also set of the session on given ASBR with the all transit providers. And then the abstract next hop will, there is a way through the transit provider. Or it could be a set of session from given site with given PRAS, right? So we say doesn't matter which of ASBRs at site has the active session with the given PRAS. At least one is there. We keep advertising these as a BGP next hop attribute. Concept is very generic, and there could be also other use of them. I'm just working on some other use of the abstract next hop, but let's see how this would work in our example network, right? First, look inter-site, how this will behave between ASBRs, core routers, and route reflectors. And for this example, the abstract next hop represent the all sessions with the AS2. AS2 is on the bottom right from given ASBR. So each ASBR, therefore the IP address would be specific and unique for the my ASBR and PRAS. I call it APA abstract next hop. ASBR PRAS specific abstract next hop. So with that, each ISBR advertised the one path to the prefix 2 with the next hop, BGP next hop set to abstract value associated with the advertising ASBR, as you see on the picture. So abstract next hop 1.1 underscore 2 if the PRAS is 2, underscore 3 if the PRAS is 3. And then the root reflectors are doing the re-advertisement to the core routers. And they are doing that with the add path. So all 4 paths are reachable, are visible to the core router. Actually, the good idea is to have one more path, and we'll see later when it comes to play. Having that information, core router can load balance traffic, egress traffic, egress downstream traffic across all 4 ASBRs in the example. So how this will behave in the failure scenario? The first simple failure, come on, is one session between AS2 and ASBR 1.1, and in this case, BGP next hop would not change, right? Because we have another session. There is no need to send update to root reflector. This is more like a next hop self to the loopback. The same, the rest of the network will not see much here. The next could be, okay, what if I don't have a second session? So the example now is AS3. And ASBR 1.2. We lose the session. This is the only session to add that ASBR to the AS3. Therefore, BGP next hop has to be removed from IGP. When it's removed from IGP, the core router immediately sees it. Immediately is everything has time, but it's much faster. It's a one operation in the ISIS or in OSPF, right? And based on that, the one of 4 paths used previously by core router is not valid anymore. And so one operation which triggers local convergence or local path selection on the core router without need of propagating BGP updates and withdrawals. And if this device has something pre-programmed in the FIP, then it's possible to do this even in sub-seconds for the hundreds of thousands of millions of prefixes. Another example, what if we lose all session between ASBR 1.1 and AS2? The abstract next hop now has to be removed from IGP because there is no more session on ASBR 1 with AS2. And the story repeats, right? We just remove the next hop from IGP. This triggers the local fixing on the core routers and rest of the network. And the final doom day, we lose all. We lose all sessions on all ASBRs with the AS2. Of course, all BGP next hop become unreachable in the ISIS or IGP, and core router just removes the 4 of them. Now the 5th path become interesting because core router can send traffic to other exit at other site. With all these failures, after the fixing happens and the traffic is restored, there is a normal BGP convergence. There is a withdrawal. There is a path updates, but our traffic restoration do not depend on that time. So what if we just stop here we'll see that all 4 ASBRs are visible across the entire network, and we have the same challenge as before with the fact that we have only one update going out of my site to another site. We have to renew it, send the update with the new BGP next hop. So let's make another step of abstraction, and whenever the update is leaving my site, let's change the BGP next hop to another abstract address, which now will represent not all session per ASBR, but all session of all ASBRs as a set. And you can easily find 2 things, right? That first of all, we advertise only one path, regardless of number of the ASBRs at site, which is good because this reduces the scale on the network-wide scale. And second, it doesn't change if one of the ASBRs lose his connectivity with the neighboring AS. And again, how this operates under the failure. The single session fail, there is no withdrawal at all, right? No update at all. Next hop doesn't change. If we lose 2 sessions from the if we lose 2 sessions from ASBR 1.1, there is a removal of the abstract next hop, which is specific to ASBR 1.1 inside the inter site, but from the inter-site update, the next hop doesn't change. So there is no need to do anything out of the given site. One note, there could be, and there is a possibility that the update need to be sent because originator ID change, for example. But because the BGP next hop is not unchanged, there is no need to do any FIP programming or FIP changes. And if we lose this all session with AS2, like that, then obviously we have to withdraw this site-specific or site PRAS specific BGP next hop, abstract next hop from network-wide IGP, and that force us to use the backup exit. So what would be the results from the scale perspective? In the same network with the same environment, the CR needs to handle between 2.5 to 10 million paths. That depends a little bit what is the ECMP on the one side of your network. So in most cases, it would be 2.5 million, not 80. On ASBRs, we need like a 3 million path, maybe 10 million in very worst case scenario, where 5 other remote sites are in equal cost, right? So rather, I don't know network which gives me that characteristic that 5 remote sites are in equal cost from me. So I do the ECMP that way. But we may save like 80% of the path. This part which I previously said, it's never used, it's unneeded. We not propagate it. We have quite good ECMP, right? If we are going to reach something out of my site, and we may have up to 24 ways, right? With the at path 5, right? So provided that these site 2 to site 6 are in ECMP, they are in the same cost, IGP cost from site 1, we spray the traffic coming at site 1, we spray among 3 core planes in this example. And then each core planes, when delivered to egress site, is sprayed over 4 ASBRs. And then this is sprayed, this goes to the PRAS. opposite is a four-way because that's what we, if the egress is local to site 1, we have 4 egresses. And finally, the configuration. So this is an example of Junos. We have this quite specific construct here, just for convenience. Under egress TE, we can give the IP address. That's exactly address used by, this is the address of abstract next hop. And this is a part of BGP configuration. So this address is inserted in the routing table as of family ARP, only if we have at least one neighbor up and running. Most precisely, it's in established state, and we already received end of RIP marker. So we even know that it's converged. And then, of course, this address needs to be leaked into IGP. This is a simple policy, and that's it. So as a result, we see the abstract next hop 1112 in the ISIS, in this case, IGP link state database. And in BGP update, when the ASBR advertised the prefix 150.0.0.0/24, the next hop is set to abstract value. I try to make it also for iOS XR, and it's almost possible without this special knob. It's almost possible because, but it's possible with iOS XE. So the idea is that the abstract next hop address would be a static route, tied to the interface, and the next hop of which is the IP address, this 11.1.1.1, 11.1.1.5. It's an IP address of my remote peer, external peer. So if the interface goes down or the ARP resolution for the peer go away, also this static route go away. Then we need to re-advertise this into the IGP. And here is a trick, right? I can do that, but the fact that the address of peer is reachable doesn't mean that the BGP session is up and running. And the only way I found to mimic that is, okay, I know that this session should give me some leading prefix. In my case, it's 57.57.1.1. So if I get that from the session, I know the session is up. So this is a condition, the condition here. You can simplify that, remove this condition, and say, okay, if the interface is up, then the abstract next hop is up. The rest is the same, right? BGP update is setting this abstract next hop address as a BGP next hop, and the logic is exactly the same. And finally, third example is again from Junos. I'm a little bit more familiar, but you remember I said it would be good to make another level of abstraction when we advertise out of the site, right? So now we create the static route, which is this site peer specific abstract next hop, and we will advertise it back to ISIS on the ASBRs only if I have the specific ASBR ANH in the routing table. So if we come back to, you see that ASBR specific abstract next hop is 1.1.1.2, and here at the bottom bottom left, I have a condition. There is a condition which says if 1.1.1.2 exists in the INET 0, then policy will redistribute the static with tag 2 to IGP. And of course, I may have more conditions like that. So I can check the ASBR of the abstract next hop of ASBR 1, 2, 3, and 4. And if one of them exists in INET 0, then I will redistribute the site-specific address abstract next hop to the ISIS or OSPF. So then you can see in the link state database that this site PRAS specific abstract next hop is in the routing table in the IGP routing 1.0.1.2, and this is also what a route reflector advertised as a BGP next hop to another sites, not locally to clients, but to other route reflectors at other sites. Okay, so short summary. The scale-out architecture solves some challenges with bandwidth redundancy, round-trip time, also may help with the commercial side. The cost of scale-out is always the control plane states. They are going up. So we need some new practices, new construct, how to deal with that. And abstract next hop is useful construct. It's a tool. It's not a holy grail. It's not something which solves all the problem on the earth. One of my colleagues commented that, oh, it doesn't solve the optimality of the BGP routing. Of course not. It's not for that. It's a tool which allows you to control the scale of BGP path across your internal IGP cloud. It's just and the use of it is documented in the draft. I submitted it for the IETF Grow working group. So you can comment, bash on me, fix it, and make it usable for others. Thank you, and it's your time for questions, if any. Peter, you promised grill me. What about the best guess protocol? Come on.
So your example is essentially...
Speak to Mike. Mics are on the back. Or I can give you.
Justin Ryburn with Kintic. Your example is essentially a service provider scaled out peering with other AS's example, but given that it's a spine leaf topology and the fact that a lot of our modern data center designs are BGP spine leaf, is this something that would be applicable in the data center as well, you think?
Yes, there is a possibility to make it applicable for the underlay routing in a spine and leaf. The thing is, it's not for free. There is some cost, operational cost associated with that, right? We need to configure these IP addresses, etc. So depending on the scale, right? If your network, if your clause, IP clause has, say, 10,000 prefixes, not 100,000, 500,000 prefixes or million prefixes, is it worth to do that, right? But yes, it's possible. It reduced the how far in the how high in the closed network this the update has to travel to close the traffic.
Yeah, it seems like in that architecture you typically run into models of networking devices that have a limit on the control plane even more so than you do in the service provider edge networks, right?
Actually, I don't know. Again, one person which commented my draft said, you know what? Who cares about control plane performance? There is no problem at all.
The people who are trying to do sub-second failure redundancy.
The sub-second is always about the pre-provisioning state before, and yes, then it's useful. If you are looking for the sub-second, that could be useful because we remove the one object which fix the tens of thousands, if not hundreds of thousands of the routing entries. But your hardware has to have proper indirection, so not every hardware can do that. I know that if we have only two levels, as on the example, most of the merchant chips, including Trident, Tomahawks, and all these, can do that. But if the indirection depth going farther and farther. So VPN over BGP-LU over a tunnel over another tunnel, then things become a little bit more complex.
All right, makes sense. Thanks.
Yeah, the example is service provider. You can think about this also from the content provider, which peers with the service provider and want the bandwidth, right? Network is network. BGP is BGP. Doesn't matter is service provider or content provider. Another?